Hello, I am Juling Li from the University of Hong Kong. Now I will introduce our recent work towards unified 3D object detection. This work is an extended version of the paper UniMODE, Unified Monocular 3D Object Detection. In this work, besides the original content in UniMODE, we build the first unified multimodal 3D object detection benchmark UniMODE 3D. Then, we developed the first unified multimodal 3D object detector, namely UniMODE, by extending UniMODE to its multimodal version. In our previous video, we have introduced our developed unified monocular 3D object detector UniMODE. Now, we expect to extend it to its multimodal version to address the opposed nature of monocular 3D object detection. However, there is no unified multimodal 3D object detection benchmark. To bridge this gap, we first build the first benchmark UniMODE 3D based on the data in the Sun RGBD, ArcitScenes, Objectron, Hyperscene, Kitty, and NuScenes datasets. For the entire benchmark, the data sample numbers of the training, validation, and testing sets are about 175.6K, 19.1K, and 39.5K, respectively. In UniMODE 3D, we investigate significant effort in unifying the data formats of various datasets and evaluation procedures. To unify this benchmark into an online perception format, we remove all depth points invisible to the camera view at the current timestamp and only retain the visible points. This slide presents the overall framework of the unified multimodal 3D object detector UniMODE. The pipeline of UniMODE is illustrated as this figure. As shown, the detector takes an image and a point cloud as input. The image is captured by a camera, and the point cloud can be collected by any kind of depth sensor. An image branch and a point branch are constructed to extract features from the image and point cloud separately. The image branch of UniMODE is the same as UniMODE, and its output includes the image BEF feature, domain confidence, and M+ inquiries. For the point branch, the input point cloud is first voxelized into 3D voxels and then processed by a pillar encoder employed in second. Next, after the pillar scatter operation that transforms the obtained feature as a BEV feature, a point network is employed to generate the point BEV feature. Obtaining the image and point BEV feature, we fuse them with the proposed mic module, which enables the image BEV feature and point BEV feature to complement the information of each other, and the multimodal BEV feature is derived. Subsequently, 1 encoder and 6 decoders with the same implementation as UniMODE are employed to generate detection results based on the multimodal BEV feature. We conduct extensive experiments to verify the effectiveness of the proposed techniques in this work. Specifically, we compare UniMODE with several representative multimodal detectors on the UniMODE 3D benchmark, and the results suggest that the performance of UniMODE is promising. Besides, it can be observed that UniMODE outperforms UniMODE very significantly, which suggests the effectiveness of incorporating depth sensor information. We also visualized some detection results of UniMODE, and it can be observed that the result is promising. Thanks for your watching, and please feel free to contact us if you have any concern.